So what we are going to do today is, one, we are going to look at some examples on the application of Wick's theorem. We are then going to also express these contributions diagrammatically. And the examples which we are going to use are going to serve as a motivation for redefining the vacuum. Because you will quickly see that even with free particles, to calculate the expectation values and transition probabilities becomes unwieldy. So most of the operators which we are going to deal with will at most be of a two-body type or a three-body type. And with only those types of operators, it means that we, by redefining the vacuum, we can actually simplify the calculations. Now, I'm going to use the exercises this week as a model to motivate the introduction of this new reference state. And this is going to lead to something which in the literature is called the particle hole representation. So it's just us technically redefining the vacuum. And that means also that we have to adjust a little bit these contraction rules so that we can actually deal with particles above and below the Fermi level. Now, this is the kind of standard way by which you would typically deal with many body systems in atomic physics, molecular physics, or general quantum chemistry, in condensed matter physics, nuclear physics, and essentially all applications of these methods to physical systems, where a low energy approximation without dealing with relativistic quantum mechanics is a viable approach. So essentially the methods which we discuss here, when we now are going to introduce more particles, you will find them, you will find it unpractical to actually calculate all these expectation values by setting up all the particles as active particles. This also paves the ground for making approximations to the state of a given system. So it's sometimes it takes some time to develop the physical understanding of all this jargon, but hopefully you can see from the calculational recipes which we're going to develop that this simplifies the calculations. And we are always looking after ways to simplify the calculations. And typically the so-called second quantization or number representation or Fock space representation is a way by which we have tried to reduce the complexity of a many-body system by freezing out spatial degrees of freedom and perhaps also spin degrees of freedom if needed. So let me quickly remind you, very quickly, about the Wick's theorem. So this is just a 5-minute short reminder. And then So the Fock space is now defined in terms of all particles which can occupy specific quantum mechanical states. That's the way you define the Fock space. So that means that you're counting only the representation of number of particles in a given set of single particle states. So it's not like you are setting up a tensor product of a spatial part and a spin part, but now your tensor product is just a tensor product of states being occupied or not. So this is how you would define Fock space. And then when you calculate the different integrals, which we often loosely call for matrix elements, because we often end up with a matrix representation of specific integrals, then that is where you would reintroduce these degrees of freedom, which you have left out. So in practice, that means that we are simply counting the number of particles which occupy a given single particle state. Okay, so let's quickly remind ourselves about some of the basic operations which we have looked at. And also one thing, if you've, we discussed last week about the exercises, if you think I'm going a little bit too fast on the whiteboard, please stop me. So what we have, just a quick reminder, we have these contractions, and this is the only one when we deal with a true vacuum, which is non-zero. And mathematically, what we are doing now is that we are calculating this quantity here. And then we have 3 more contractions which are 0. So this is the only one which is non-zero. So we have this one, and then we have the one here where this is a creation operator, and this is again equal to AP dagger AQ. And these contractions are all 0. Now, one thing which we are going to do now, later today, is to redefine this one. We will redefine this contraction, and we are going to let it be non-zero for a specific case, because we are going to introduce a new vacuum reference state. Okay? And that is hopefully going to simplify the calculations. Now, Wick's theorem, which we then set up and discussed last week, simply says that if I am now calculating the expectation value, in this specific case, the vacuum to vacuum expectation value of this quantity here, this is just given by the sum. There's only one term which can survive. And M is the number of operators divided by 2. So that means that we have to pair creation and annihilation operators. So if you have an odd number of operators, this is automatically equal to 0. And then we have the set of all contractions. So all contractions between pairs of operators. So we have X, Y, Z, up to some W. And then we just label this one by putting all possible types of contractions. So that's all possible contractions which we can have. Now, one of the things which we also introduced last week is what's called Wick's generalized theorem. Now, due to the contraction rules which you have here, it means that there are lots of no, this is just a single sum. Yeah. All possible contractions between pairs of operators. So it's a kind of a little bit sloppy notation, because you have to set up all. It's a compact way of simply indicating all possible contractions, and I'm going to show you some of them. Yes, annihilation or creation operators. So I'm just setting this up as a generic. So X could also be a set of several creation and annihilation operators. So what we have to do at the end is actually to contract all pairs of operators. And that set of operators has to be given by an even number and an equal number of creation and annihilation operators. So if you see immediately a term which you have to evaluate, where you have a different number of creation and annihilation operators, due to these rules here, then that is automatically equal to 0. So let's just remind ourselves of Wick's generalized theorem, because when we are setting up states, we are actually setting up states and operators in what we call a normal ordered form. And due to that, it means that contractions of the type which you see here are the only ones which survive. So if you're trying to make contractions inside an operator which is normal ordered, then you will have contractions like this and this one, and they are all 0. So in Wick's generalized theorem, what you have then is that this expectation value, X, Y, Z, up to W, the only term which survives, and we are now going to write this as a specific string. So there's a string now, so you could think of X and Y as being a string of normal ordered operators up to a given number. So I'm just rewriting this X, Y, Z, W in terms of a string of normal ordered operators. Then there can be a new string of normal ordered operators, which we just last time labeled B1, B2, up to some operator. And then we can continue with this C1, C2, And this could continue. And now the only terms which survive are the terms where we have contractions between the operators, but the contractions inside the operator are all zero. So that means that we would have contractions like this continues, this goes on, so all these are contracted. Now, the example which we had last time was an example where we took a two-body state. So let's just repeat this, because we will also remind you of the type of diagrammatic representation which we can make, which is a very compact way of setting up these different contributions. So the example which we looked at last time, so let's remind ourselves of that. So we had a specific state, ij, which is ai dagger aj, acting on the true vacuum. So you can say that this state is already normal ordered. So because we have creation operators to the right, now to the left, and annihilation, in this case none, to the right. Similarly, we had another state, KL, which is given by AK dagger AL. So this is also normalized. And then we looked at the two-body operator, which is given by 1/2. And this is just a sum over all the possible single particle states, all possible ones, which you have used to define your full Hilbert space or an effective Hilbert space. And then we have the integral RS. And then we have AP dagger AQ. And what you see now is that these operators also are normal ordered with respect to the true vacuum. So you see in this particular case that we have the creation operators to the left and the annihilation operators to the right. So the terms which we're looking at are all normal ordered. So that means that instead of us going back to Wick's theorem here, where we have to list all the possible contractions, we're only going to look at the contractions between normal ordered chains of operators. So let's look at the explicit calculation of that one. So we take this operator, which represents the interaction energy of the system, and we are going to calculate Ij of H of I of KL. So let's just repeat this one. And then we are going to introduce later the three particle case, which we discussed also last time. And already that one will serve us as a way to introduce a more compact notation. But let's look at this one. And in this specific case, if we write everything out in full glory, we would have PQRS. And then we have the integral, which we just leave outside here, of VRS. And then we have this string of operators. So in this case, this is AJ, AI. So you can say that this set of operators is already normal ordered. So I'm just going to put them like this. And then we have the two-body operator itself, AQ dagger, AS, AR. And this is multiplied with AK dagger, AL, acting on that state. And if we now look at the operators, you could now think of this as three sets of normal ordered operators. And if we do the internal contractions here, like this one, this is 0 due to the rules which we have. If I try to do a contraction like this one, this is 0. If I try to do one here, that is 0. If I try that one, that is 0. So the only contractions which survive are those where we link the different normal ordered operators. So that simplifies the usage of Wick's theorem due to the contractions which we have defined to be non-zero. So normally what you do then is simply that you set this up. AQ, dagger, AS, and AR, and then AK and AL. So this should be an L actually. So as we said last time, it's pretty common to skip the zeros, the vacuum states, and simply just look at the contractions. And we have already done this. So one set of contractions is this one and that one. So this is non-zero. And then another one is this one and that one. And then we will have a contraction like this. No, sorry, not that one. Like this, and that gives rise to a minus sign. We can keep this one. Then we can do this contraction. This is another non-zero one. We keep this one and that one. And the final one is simply to have this one. And then go back to the first one, which we looked at on the right-hand side. So these are the possible contractions which we can get. And when we bake in the different Kronecker deltas, what we get then is that this gives rise to the contribution Ij, and then we have V, and the next one is KL. Here we still have, but we have a minus sign because we have to interchange two operators. So we have LK, and then we have, in this particular case, we have two minus signs. So we get Ji and Lk. And finally, we have a minus sign here, which is a Ji of V of KL. And what we did, I think that's almost 2 weeks ago now, is that this term is the same as that one. And this term is the same as that one due to the fact of this being identical particles and that the interaction is permutational invariant under the exchange of two particles. So then this integral here is the same as that one, and this one by just interchanging I and J, which are also dummy variables. Now, if we do that, then we got the final expression for this term, which we started with. So the final expression for that specific expectation value, if we go down, so let's just single this out as an intermediate calculation. So what we get then is that this is equal to Ij V of KL minus Ji of V of KL. Now, let's go back to the, as an intermediate step now, let's look at the diagrammatic representation, because that gives us a compact way of setting up these contributions to an expectation value. So let's quickly remind ourselves of some of the things which we discussed not last week, but the week before. Diagrammatic representation. So what we did then was that an operator like this one body operator, which is given by PQ, and then we have an integral Q of AP, AQ. This is something which we would represent without putting arrows on it, because we haven't done the contractions. So it's pretty common to leave out the arrows, but you would put labels on them. So you would have now an interaction vertex here. And in this specific case, this is now meant to represent this term here, where the incoming state is now given by this one, Q, and the outgoing state is given by P. But we don't put arrows on them because we have left these uncontracted. So this is just a way to represent a one-body operator. Now, whether you have the mirror image with that one here, doesn't matter. Okay, so that was one way to represent a one-body operator. And whether you want to, the way you draw it is up to you. And for those of you who have taken a course in quantum field theory, this is also something you will encounter. And these terms are typically called vertices, interaction vertices. Then for the two-body case, what we had is an operator of this form here. And then we have a sum of a PQRS. And then we have an integral PQ of VRS. And then we have the chain of creation and annihilation operators. Diagrammatically, the way we represent that, and this is a time-independent interaction. As soon as you come into quantum field theory or field theory in general, you will also add a time dependence, but we are going to think of these as instantaneous interactions. And then typically what you have then is that this operator here is then represented by the outgoing state here, PQ. So we have P here to the left. So the first one is to the left. And the second one is to the right. And then we have the next state here where we have the indices R and S. So what you would do then, depending on the type of operator, you would simply put labels on all the legs, but we have left the legs uncontracted. So if you now look at a contraction like this one, then we would represent that in the following way. So we have a state P, a state Q, and this contraction can be written like that. Or what is more general, you just write it like this. So this is actually a delta PQ. So that becomes simply P. And then you will put an arrow. So in some textbooks, people like to have arrows which flow from left to right. Others do up, down. This is just a matter of taste. Whether you like to have things lying or things going up, that's up to you. I normally work with time-dependent theories, and then I like to think of time as something which propagates upwards. But you could also think of time as something which propagates from left to right. This is, I'd say, just a matter of taste. Whether you have them lying or standing doesn't matter, as long as you agree upon what it means. Okay? And this, yeah? Yeah. Oh, sorry, that is, I actually wrote it wrongly here. So that should be PQ, sorry. That's the outgoing state. And then this is the incoming state. Thanks. So if you now go back to the interaction which we had here, where we calculated the expectation value, you see now that for this specific case, we have two terms. And where this leg has been in, these two lines have been interchanged. This is actually us having done a contraction. So we can break this down. So if we now go back to this expectation value we looked at, what we did then was to calculate this one, V of KL. So in principle, what this is, you could now think of, so this is just pictorial, and often people just skip what I'm drawing here, but you could think of this as being your vacuum state, and then you have created a state, KL. So this is your state AK, AL, acting on the vacuum state. Then you have the interaction here. So then we have R and S, P and Q. And finally, this returns to the state here, which is AJAI. You could just draw it like this. And we put labels I and J here, like that. And then we can, what we do now is simply just to draw pictures, right? So we take and perform that contractions. We can do that contraction, and then we can do that one, and we can do this one. And this is actually the kind of procedure which we often use because this is now meant to represent the contraction which we put up, which gave us delta PI. So this would be the first term which we had. So if you spool back a little bit, if you look at the first term, that is this one, diagrammatically, we can then represent that as this set of contractions. So this would be the one you see here is this one. Then this contraction is delta JQ. This contraction here is delta RK. And this one is delta SL. So when I bring everything together, I get the following term. So when you look at this one, when I now put labels, I would have an arrow here. I have the interaction element. And this means that I have IJ here, and then I have KL coming in like that. The next case I can do is just to draw a new contraction. So I have the IJ here, states, and then I have my operator, and then I have my states KL here. These are the outgoing states. I can still insist on contracting these two guys and these two, but now I could contract this one with that, and that one with that. So putting on labels P, Q, R, S, this gives me a delta KR as before, a delta SL. So these are the terms which you see here now. Delta KR is this one, delta SL is that one. But now I'm interchanging, so I get a delta PJ, and I have a delta IQ. So delta PJ is this one, and delta IQ is that one. So if I then go back to my contractions, which I put up here, if you now look back at what we had in this set of contractions, that would correspond to the term where I now leave this one unchanged, but I actually change these two. So diagrammatically, the last term here is now going to give rise to a, so this gives rise to a matrix element IJ VKL. This one is going to give rise to a matrix element which goes like JI VKL. Here it has a minus sign. Now the way we indicate that graphically or diagrammatically is as follows. So what we would have then would be a diagram which now looks like this. So we have the previous case, which is given by us having K and L. But now we cross the lines. So every such line crossing gives us a minus sign. Now I can switch the lines which you had here as well and do that. Then I would get the equivalent of this one. And then I can keep these two fixed with P and J, but then I could cross these two. And then I would get the matrix element with a minus, and then I would have IJ, but LK. And these would be the other two contractions. So in total then, what I could do, when I look at this expectation value, IJ of H of I, the interaction, of KL, which I wrote like IJ when I did the contractions mathematically, then I have to actually evaluate this integral, minus JI VKL. Diagrammatically, you would write this as two distinct diagrams. And you would simply put a plus sign on them. But then, since you have a crossing fermion line, you have to, when you want the actual element, the mathematical expression, you have to put a minus sign. So every crossing fermion line represents now two operators which have to be transposed with respect to each other. So we would have an IJ, we're putting labels because these now represent specific contributions to the energy. And KL, and then I would have my IJ here. So these are normally called, in non-relativistic quantum theory, they are typically called Feynman. Now it's going to be interesting to see whether it still translates it as fireman, because that's been, when I do the Google translation here, or the Google actually acts on on my voice. It has often translated this into fireman. I don't know why. Maybe it's my way to pronounce it. So these are called Feynman-Goldstone diagrams. Now, we discussed also a more compact notation where we could actually bring together what we call the direct term and the exchange term, which is this one. We can just bring them together in what we call an anti-symmetrized matrix elements. And then we can bring together this notation here into just one diagram. That has its own name. It's called Hugenholz diagram. So let's just bring that up because that gives us an even more compact diagrammatical representation. So the next step is to remind ourselves that we could redefine these integrals with the direct term and the exchange term in terms of just one. And if you're thinking of storing these, this is something which is very convenient because then you just, if you can evaluate the integrals before, you start running the calculation of expectation values, then you can store this and just look them up in a table where you are just taking together the direct term and the exchange term. So these are just two-dimensional integrals. If you are in one dimension for each particle, if you have one particle in 3 dimensions, then these are 6-dimensional integrals, etc., etc. So diagrammatically, that leads to something which is called a Hugenholz diagram. And in that case, the way we would draw it is just to shrink the vertices just into a blob or just a box like this one. And then you would simply draw it like this, where in our case you have ij coming out, and then you have kl coming in. So you just bring together the two. And then you can decide the way you open it up. Sometimes it's actually confusing because people sometimes actually imply that they are using Hugenholz diagrams with anti-symmetrized matrix elements, but they list the diagrams in the kind of standard Feynman-Goldstone style. So unless the authors have specified properly what the interaction looks like, then sometimes it can be a little bit confusing. So this is a typical example of how we could actually extract the same results without doing any calculations. Because this kind of graphical way, which you see here, where we now just bring together the different lines and think of them as mathematical contractions, these contraction operations, then by doing that, you can reduce all the mathematics to drawing diagrams. And this is one of the strengths of the diagrammatic approach, which people like Feynman introduced back in the end of the 40s when people developed quantum field theory. So it's an extremely powerful way because by just looking at a diagram like this, you can say this represents this and this type of physical process. These are two particles coming in the states K and L. They interact, and then the interaction modifies the states they move in. And then the end product is a state I and J. So you will see that, especially in particle physics, it's very common to ascribe a physical meaning to specific processes, to specific diagrams, sorry. Yeah?
So the matrix elements in relation to particle physics,
yeah,
they're usually called doublet clusters.
Yeah.
Should we be calling them that?
No, because if you think of particle physics, you're thinking of the vertices, which are called coupling constants. So, but the vertices can also have a more complicated expression than just a constant times something. So in our case, this is just the way to think that there is an interaction between two particles taking place at a given time. And if you do particle physics, you can have a specific decay processes taking place at one time, and the next time they propagate through a meson, which is being exchanged with protons and neutrons, for instance. and then you have two new protons and neutron pairs which come out, etc., etc. So the vertices then are normally used to describe specific physical processes. Whereas in our case, the way we are going to look at the vertices here is just a way to represent a two-body interaction. And these two-body interactions in non-relativistic quantum mechanics, they are normally seen as what we call instantaneous interactions. So there's no time dependence in them. You can make life more complicated and add time dependence, and then you could do time-dependent many-body theory. And that's a possible extension of what we're doing now. But I think this course is only 10 credits. So there's a limit to how much we can put into it. Okay? I hope you don't get offended. Don't put in everything into it. Okay, so what I want to do now is to, before we look at the exercise this week, I wanted to bring an example as a motivation for why we should try to change the vacuum state or the reference state. So let's look at a new application of Feynman's Wick's theorem. So suppose now that we want to look at the free body state, but we have a two-body operator. Actually, this is a simple case, but even this simple case is going to be a case where we have to pay attention to all the possible permutations which can take place. So suppose now that we let's write it down here. So we have a state A1, A2, A3, acting on a true vacuum state. So this is just 1, 2, 3. And then we want now to calculate the expectation value of this quantity here, 1, 2, 3. And then we have a two-body operator, which in our case is just the energy operator, or the interaction between two particles. So this is the quantity we want to evaluate. Now, what I'm going to do now is to jump immediately to the set of contractions which we need to make. So let's just look at the contractions here. So we have the operator APQ, and then we have AS, AR, and then we have A1 dagger, A2 dagger, A3 dagger. So this is actually going to be the simpler case, because if I have different single particle states on the Bryan and Ketz side, we have more combinations which we need to take into account. And then we would have 0 here, and then we have A3, A2, and A1. Sorry, A1 here. Now, in this particular case, the operators which we have, these ones, these two operators, creation and annihilations, they act on only a pair of creation or annihilation operators. So it means that the one possible set of contractions which we can have is these two guys here being contracted with these ones. So that gives me two possibilities. So it gives me delta S and delta 2, no, delta S2, and delta R1, or if I interchange, I can get delta S1 and delta, this should actually be distinct, it's OR, and delta R2. That's one of the contractions I can make. Then what I could do now is to take, no, not that one, but this one. I could take this one, but what happens if I take these two together with that one? What would I get then? That's a possible contraction. But then there's one which is left out, which is A2 here. It's not acted upon. And then I would have to contract A2 with A3. And 2 is not free, so this is 0. So if I were to change these to, let's say, a generic state, IJK, and then LMN, you see that there are more possibilities. When I act with the operator on 2 of the states, like this one, then the one which is unoperated upon, like this one, has to match the other one due to the orthogonality of the single particle states which we have defined. Okay. So in this particular case, we see now that this type of contraction has to be 0 because 2 is not equal to 3, at least as far as I remember. So let's now just wipe that one out and this one. So if I now look at the possible contractions, so if I take these two guys, I can pair them up here. And that means that I have a delta 3, which obviously has to match 3. And then in this particular case, I can have delta P1 and delta Q2. And then I can have a delta P2 and a delta Q1. And these set of combinations give rise to 4 different terms. So if I bring everything together, this interaction will give us a delta 3, and then it's going to have a matrix element, or an integral, 1, 2 of V, 1, 2, minus 2, 1, V, 1, 2. So that's one of the possible contributions. So when I do this diagrammatically, I have to write up a 3-particle state, which now acts with a 2-body interaction. So if you have written this down, let's just wait a little bit till everybody has written it down. So this is the explicit result we get when we perform the contractions. You see clearly here that there are 2 more terms, which means that there has to be 1 with 1 free, and where 2 is left out. So this case which you saw here is 1 teaming up with 2, so the interaction acts on 1 and 2, and 3 is left out. And then there is an additional one where I have 2 free and 1 is left out. So these are the only possibilities which we will have on a free body state. These are the 3 terms which are non-zero. If you now were to replace this with a state here, which is different, or rather 2 states which are different, which still gives a non-zero contribution, then you have to be a little bit more careful because you will get more terms to look up. Now, is it okay if I don't show this because it's pretty obvious what happens? Diagrammatically now, what we are doing is to have these states here. So we have 1, 2, and 3. So this is our vacuum state. And then we have same going out, 1, 2, 3. So this is our state, 1, 2, 3. This is our state, 1, 2, 3 here. And then we have the interaction with P and Q and R and S. So that means that the first element we saw is actually this one being contracted with that, this one with that, and that one with that. And finally, this one has to be contracted with 3. Now, the case with 3 particles is something we can write down. But if we do 4 particles, this is going to start getting boring. And if I have many particles, that means that you will have to look, even if you do it diagrammatically, which is a simplification, you would then have to add, let's say you have 4 particles here, then you need to look at those combinations. So you're getting more and more combinations here, right? And if you do this either contraction by contraction or diagrammatically, it quickly starts getting unwieldy. And if you have 10 particles, I guess you wouldn't like to start looking at all the possible contractions with 10 particles, right? So this is actually motivating the introduction of a new reference state. And this is what we are going to do now. So I hope you see that, in this case with 3 particles, we can still do it. It's not very exciting. It's the kind of exercises which I don't like to give because it doesn't give you any new insights except you playing around with the different combinations. If you do 10 particles or 100 particles, which is a more common case, we are going to get zillions of contributions. And it's not fun, I guarantee. So can we introduce a more compact notation? That is the topic for after the break. And that is going to lead us to define a new reference state. But what I wanted to do is actually to use the exercise this week as a motivation for that. So I wanted to state or discuss a little bit the exercise which we have suggested this specific week, because it has some other interesting technicalities and theoretical manipulations which we can do in order to get the eigenstates of the system. Okay? Good. So let's take a break. So let's just stop the recording. So one of the things I wanted to discuss now is the model which we are going to look at, used as a kind of pedagogical many-body model. It also has a lot of nice, for those of you interested in group theory, there have been analysis in terms of group theory of the model, etc. It allows us to describe many of the basic physical processes, and it can be solved numerically in all cases, and it can be solved by using angular momentum. And that means implicitly group theoretical considerations. It's a model which allows us also to build up intuition about what is going on. As for simplifications, when we go beyond two particles, because when we're going to calculate, it's going to be pretty boring. So let's take a look at the model itself. So it's called the Lipkin 1960s. It's simply known as, so this is an intermezzo, which we are going to do. And it's normally just called the Lipkin model. So it was introduced by people doing nuclear, the type of interactions which you would have in a system like a finite nucleus. Look at now, and that's the one in the example, is that we have 4 particles, and we are going to have n is the number of slots where we can place the particles. So you will meet another model later. So we're going to have a quantum number which we call p, and that quantum number is going to be the same in each level. So you can think of each slot now as representing a specific quantum number, which we now just label represent an orthogonal basis. And this state has in addition spin, sigma, state. And you would typically also see this just depicted with a downgoing arrow. And this quantum number p, which we just leave undefined, whether this is or whatever. It's just a quantum number which now makes our state or basis. A single particle state now is now going to be defined by the quantum numbers p sigma. Now, up here, we have the same boxes, the spin values, so we just put that to +1, and we would typically label that with an upgoing arrow. It's something which we can represent with an ansatz as the one where we have filled in the system. So, and you will see why, just in some few moments, why this is a good ansatz. C1, dagger, and then it has spin down, A2, dagger, spin down, A3 with a spin down. So now I am adding to the states, not only this, and instead of writing just a minus, which can be sometimes confusing, I just put the arrow. The ansatz for the ground state, and obviously we should not forget that this is obviously acting on the Schubach. Thing which we can do rather quickly now is to calculate the expectation. So what we're going to have then is a operator H0, which is now going on. And then I'm summing over the degrees of freedom like spin. And then I have an AP that this is the H0 equivalent of what we have seen before. And epsilon is just a constant, and -1. And P in this specific case is 1, 2, 3, 4. Now, if we then calculate quantity here, this is just going to be equal to the sum over P and sigma. So we have ±1 for sigma, right? So just leave it like that. So we're going to have a half. We have epsilon now to calculate this A4 spin down, A3 spin down, and then I have AP sigma dagger, AP sigma. So it's, and then I have an A1 spin down times A1, 2 spin down, like that. And now when we do the contractions and we have a string of operators here, so the one body operator is still doable, but when it comes to the two body, and then we have this term here. So these are 3 normal load operators, yeah? This one. You could just point it out. I forgot to put that one. Thanks. So there's a sigma here. Thanks. I forgot to put that one in there. Yeah. If we look at them, clearly if I have this one, Then since 1 is equal to P, this one has to go to this state here. So let's just write it out and look at the different operators only. Now you see also why I said this about redefining the reference state, because this contractions. But one contractions which we have is definitely this one. So that gives, and then sigma has to be equal to spin down. And this gives us exactly the same. And then we have to match all the other ones with each other. So this is the only possibility which we have here, which gives us a non-zero. Repeat this, where now P acts on 2, and then when it acts on 3, and when it acts on 4. It's going to give us a term which now has sigma equal to minus. So I will get minus 1/2. Surprised that when I do all of them, I get simply minus 2 times epsilon. So for that specific state, 0 of H0 of phi 0, that is going to be equal to minus 2 times epsilon. Now, which I call for phi 1, but where I have placed, and I'm going to do this in a pictorial way, and here I'm going to define the state. So the states here, they have this spin, and it means half times this epsilon. But I could think of us now having placed all the particles up here. So this is my new state, 1, 2, 3, and 4. And P is the same here, 1, 2, 3, and 4. Now to A1, spin up dagger, A2, spin up dagger, A3, spin up, vacuum state. So in this particular case, the spin is equal to +1. And calculate this expectation value here for this specific state. And you look back at what, so in the lowest lying state, we found minus 2 epsilon. If you now look at, without having done this expectation value, yeah, +2 epsilon, because then the energies of every particle gives it to be 2 epsilon. So if you follow this kind of thinking, what you could say is that if we now have a state which we define as phi 0 is a state with lower energy than the one which we define as phi 1 of interaction. But what we have done here is actually to promote all particles. Up in this n is equal to 8 slots, P equal 1, 2, 3, 4, and 2 spin values. And with n equal to 4, then what we are going to get is a total number of configurations. So way to standard combinatorics with the replacement. This is going to be 4 factorial, 4 factorial. And that is when we are going to discuss our first many-body method, which is full configuration interaction. And in principle, take all states, and we will get a 70 by 70 matrix to diagonalize, which perhaps is not the most fun one. We are going to introduce angular momentum, and we're going to 70-70 matrix in terms of blocks of submatrices, spin value, or angular momentum value. So one of the exercises, which full Hamiltonian, and let's do that first. So the full Hamiltonian, we're going to add a term. So this is a model as you want. So we're going to define a part which we're going to call for H1. My cheat sheet, so I remember what it looks like, because I never remember that on the fly. There is a term, constant V. It sums over the 2 possible values, but it sums also over P and P prime, E sigma, A P prime, sigma. So the spin has to stay the same, 1 to +1. And here I'm having a P prime, but minus sigma, and a P and minus sigma. What is actually doing for us? So if we go back to that simple drawing we had, and we put these boxes here, suppose we have initialized our system in the slots 1, 2, 3, 4. So they are here. This is filled, and this is filled. These 2 slots here. Now these 4 slots. So what we could do now, due to the formal spin, we have to go to one with positive spin, because the spin which you see here is being flicked from minus to plus, moves it to a plus. And then it's acting on 2 particles at a time. So this P prime could to here as the first one here, this one, as removing these 2 guys here from that separators here. We could now recreate them in this box here. And I'm going to use a black color here to indicate that. And that is a new Slater determinant, which now is composed of 2 particles in P1 in box 3 and 4 with spin up. Now, if we have used this to define a Fermi level, so we have a hole, And then we have two particles, if we call the states above the Fermi level, for as a two-particle, two-hole excitation. So what happens here physically is that we have taken I0, and that gives us a new state, which is A1 spin up, no spin down, A2 spin, and A4 with spin up. So I've promoted two particles below. State here is my lowest lying state, and I fill these first states 1, 2, 3, 4 energy, which I'm just an ansatz for it. Then I'm actually with the Hamiltonian acting on the slide with some constant. So let's just be a little bit more precise, because the Hamiltonian act. You see the kind of physical process we're trying to aim at? So what it means is that you can now think of a setup. So we have a 1 with spin down, which we started with, 2 with spin up. We have this interaction, which we labeled as H1. And then we have the initial state here. This more carefully, 4 lines. So I have 1 with spin down, 2 with spin down, and then I have with spin down. So this interaction now is actually taking contraction here, and 1 and 2 here in the original state are left uncontracted, are left unaffected by the interaction. Now we can keep calculating with all the states, or we can take now and redefine the vacuum, because I wanted to discuss some of the technicalities of the exercises this week. Okay, I want to set up. And that is the final one, which we are going to deal with, and that is which is given by 1/2 times W, and it still just acts. So we have AP of sigma dagger, AP prime minus sigma, but then it has an AP minus sigma, like that. So this is an operator now, which if we have these slots 1, 2, 3, 4. We have the 4 particles, so we can start with the phi 0. We are down here, and then we put up the next slots. Now that the spin is changed for only one of the operators, okay? I can state which we can produce now is since the spin is changed by only one of the operators cited up here. So we start with phi 0 here, and we act with this H2. Then this guy gets promoted, and the other one remains in that state. So I would produce a new state, phi 1, which is A2 spin down, A3 spin down, dagger, dagger. But then I have my A4 of spin up. And then I have a particle which gets promoted above the Fermi level, like this, excitation. Because this is a state which will have higher energy than the ground state, which we calculate with respect to this specific reference state. Now, when we are going to calculate the expectation values of some, because we would have to deal with 4 creation operators, and then we have to take all next week. This is something, or actually tomorrow, this is something which we now can simplify by, I wanted to go through some technicalities related to the exercise. So simple states. So in principle, I can make a linear combination of 70, that problem, and that would give me 70 eigenvalues. And the question now is, can I reduce the dimensionality? Very nice properties, is that we can now define angular momentum operator sub-blocks. So if you look also at the system which you have here, this total spins, what is the maximum spin you could have for this system if you add all the spin values, the maximum and minimum? Algebra. So what would be the maximum? So if you add all the spin values, what is the maximum and minimum value? If you just sum this, so we said that this is -1, -1, -1, -1, -4. And if we want the spin expectation value, this is normally divided by 2. So that should be -2. If you remember a little bit back from atomic physics or molecular physics, so I would have a spin project -2 at the one extreme and +2 at the other extreme. So if you think back, units should the steps go when I go from -2 to +2? Yeah. Yeah, so it's -1, right? 0. Yes. So that means that the total S value is given by 2, and it has a degeneracy of 2 times S plus 1. Representation of these Hamiltonians, I can actually rewrite my problem. It's going to be a 5 by 5 matrix because I will have 5 states. Spin projection -2. Mind you, a little bit about the commutation relations for angular momentum. So this is something which is probably a little bit important here when we are going to rewrite the Hamiltonian. So let's write it down, the commutation relations related to the exercise, but which is going to allow us to set up the problem to diagonal matrices because we are using some specific symmetries, yeah? Could you say again? Oh, yeah. So it's not charged, thanks. Let's do one thing here. What was charging? Yeah, thanks. That's perfect, because else we would have to stop. Thanks, Milton. Let me just quickly remind you of that. So you have some operators which you may have encountered this definition here, where you have a plus, which is defined as the imaginary I times the y component. You have an a minus, which is given by 1 over square root of 2. One of the physics and mathematics courses. Then we know that there is a set of commutation, angular momentum, J. I have a commutation relation which says that if I take this operator A projected on the z-axis, this is equal to minus plus of A plus minus, just suppressing that one. I have another commutation relation which says that A plus.
Sorry?
Yeah.
J is just like a thermal projection of the...
No, J is now an angular momentum in terms of a Jx plus. So these are projections on the axis. So I have an x component. And you can write an A plus here in terms of a linear combination of the x and y components. No projections, no. So these are just projections of the angular momentum on a given axis. And we have an A plus is given by 2 plus A of z. We have the commutator between AZ and JZ. J plus, and that's plus minus A plus minus. Does that ring a bell from a course in quantum? Now is the following. So I'm going to define an operator, and I'm going to define a J plus to rewrite the Hamiltonian in terms of these operators. And I'm going to show that the Hamiltonian commutes with these a sum over only P, and it has a P with spin plus and a P with minus. T is a plus and minus. So this is just a definition. And if you use that, you can also continue now, sum over P, AP minus, and AP plus. I can define a JZ, which is an AP sigma. And if you think back, Hamiltonian, you see now that this H0, which we had, is simply epsilon times this JZ over H0. If you then, and this is one of the things you're going to do in the exercise, is to calculate J plus, J minus. So it's not a too exciting exercise in using anti-commutation rules. So what you need to do then, because this would be the same as AP plus, AP minus, and then it's a commutator of AP prime minus and AP prime plus the operator 2 times JC. So that's one of the exercises. So I'm not going to things. And then if you continue along this line, what you will see is that if you now minus J plus, this is going to be the same as minus, obviously, of J plus, J minus, 2 times JC. So that's one of the other commutation relations. If you set up the commutator, so there's a lot of these expressions which you then can show that these operators which we have defined here, they behave as angular momentum operators. And that is that with these operators, and when I go back to the Hamiltonian, I can actually write, see, I can take this H1 and I can rewrite it as 1/2 times V times J plus squared plus is equal W divided by 2. And then I have J plus, J minus, plus our operator, which we defined just some weeks ago. And the interesting thing for us is that, so if I take the whole Hamiltonian, H0 or different components, you will see that this vector or an eigenstate of angular momentum is also an eigenstate of the Hamiltonian things in H1 plus H2 plus H0 and JZ is going to be equal to 0. You will see that angular momentum is something, this definition of angular momentum commutes with the Hamiltonian. So where is this going to lead us? Suppose now that we have a state with a total spin, which is -2. Yeah? Yeah. On a?
Stateless?
Yeah.
Just like just arbitrary states.
Yeah. Taking a course in quantum mechanics, you're probably been introduced to what are called the step operators. Just remind ourselves of that. So suppose now you start with a state which has spin projection equal with a minus sign. Now, there's a unique way of making that. So this is only one state, which you can make with below the Fermi level, as we defined here. All these single particle states, which you see here, are filled states. So that specific state here has now, if I want to create and lowering operators, and this is roughly where I'm going to stop now, J plus minus acting on a state like this, Epstein coefficients. Does that ring a bell? So this would be a typical coefficient with a given ms, m sigma value. There's a new state with m sigma plus minus 1. And these coefficients are given by the total spin, which I'm going to call for j here. So it's a j plus 1. So in our case, this total j, this value is the actual value which you're having. And then I have m sigma plus minus 1 square root multi plus minus, so this should be here, plus minus 1. Then what we are going to calculate is to set up these different matrix elements. And we have 5 projection values. The total spin is 0, plus 1, plus 2. So this is going to lead us to 5 different points to be diagonalized. So the reason why we do this is simply because we can now rewrite the whole Hamiltonian. It commutes with angular momentum, which you will show in this exercise, which means that the eigen-Hamiltonian, and that basis can then be used to set up the Hamiltonian matrix. And that's going to be, which is a little bit aside from what is coming tomorrow with the technicality for reducing a 70 by 70 matrix diagonalization to a 5 by 5 in a more compact way. I'm going to give you some more hints. So the exercises this week are perhaps not the most exciting one, rotation relations, but that has a nice property that we can actually use that basis with a Hamiltonian matrix. So you will see this coming back when we're going to discuss full control. I will give you some more hints about this exercise because we will continue with that next week as well, whole formalism, which is the one we will use as a compact way of expressing many body correlations. So that will redefine the vacuum state for us.